Okay, in number 5, we have this matrix A that's a 2 by 2. And we have a transformation corresponding to A. And what we want to do is find the vector x such that the transformation corresponding to A maps that vector into the vector 2, 3. Well, what do we know about the relationship between the transformation and the matrix A? Well, if I look at 2, 3, that vector, that's actually a column vector that's the first column of matrix A. And I know that the first column of matrix A is actually the way that the transformation corresponding to A transforms the first unit basis vector, E0. And so the x that I'm looking for is the vector with components 1, 0, or a 1 in the 0th position and 0 everywhere else. So now we want to find a vector y such that L of A of y is the vector 1, negative 1. And again, notice that 1, negative 1 is the second column of A. And I know that if I look at how this linear transformation maps E1, it will be to the second column of A. And that means the y I'm looking for is the second unit basis vector, or the vector with first component 0 and second component 1. Now I need to find the vector z such that L of A maps into the vector 3, 2. That might be a little bit harder. Oh, but I noticed something that was interesting. You know what? L of z is 3, 2, which just so happens to be the vector 2, 3 plus the vector 1, negative 1. Right? And that means that it's equal to L of the unit basis vector, first unit basis vector, plus L of the second unit basis vector. But since it's a linear transformation, oh yeah, that means that z must be e sub 0 plus e sub 1, which means it must be the vector with components 1, 1. Oh, that was not so hard.